Hello, and welcome to our video on improper integrals. First, all of this material comes out of Appendices A.5 and B in the lecture notes. Second, this video is intended to be a review of some topics that hopefully you learned in a calculus class, but we'll repackage them in the notation and vocabulary specific to our course with an eye towards using all these results for the Fourier transform and the inverse Fourier transform. We begin by saying that a function f from a closed bounded interval a to b in the reals into the complex plane is integrable if the real part of f and the imaginary part of f are both integrable on the interval a to b as real valued functions, according to the definition of Riemann integrability that we learned in calculus. And we put the integral from a to b of f of x dx is the integral from a to b of the real part of f plus I times the integral from a to b of the imaginary part of f. So this is precisely the natural definition of the integral, and we've been using this definition somewhat implicitly throughout the course whenever we've taken an integral of a function on an interval a to b so far, although the fact that the function could be complex valued probably hasn't played too much of a role in our calculations. So what is integrable on the interval a to b? Well, if you dig out your calculus book, you will find a complicated but beautiful, but also complicated definition of integrability in terms of a limit of Riemann sums. And that is a good definition, that is a correct definition, and we're not actually going to use that definition at all in the course. Instead, here are some classes of functions for which the integral exists. All continuous functions are integrable. So if f is continuous on the interval a to b, its integral exists. That is, all functions in the function space C of a to b. All piecewise continuous and bounded functions. So we don't want any vertical asymptotes, but we can have a nice tame jump discontinuity. In particular, the function space C1 piecewise on a to b that we've worked with using the Fourier series convergence results. And in fact, all functions that are continuous and bounded on the interval a to b, except we might allow some discontinuities at a countably infinite sequence of points xk from k equals 1 to infinity. That's a pretty remarkable result, that a function can be continuous at all but countably many points and bounded on the whole interval, and still it is integrable. So a function can behave pretty badly from the point of view of continuity and still retain its integrability. Now let's suppose we have an arbitrary interval I contained in the reals, not necessarily a closed bounded interval from a to b. We will say that a function f from I into the complex plane is locally integrable on I if f is integrable on all closed bounded subintervals a to b contained in I. So you give me the interval, maybe it's open at one or both ends, maybe one of the endpoints is infinity, and then the function f from that interval into the complex plane is locally integrable if whenever you pick out a closed bounded interval a to b in the larger interval, f is integrable in the usual sense on that interval. So all continuous functions are locally integrable, because if you're continuous on the whole interval, you're continuous on a closed bounded subinterval, and therefore integrable there. All piecewise continuously differentiable functions are locally integrable, according to our definition of the space C1 piecewise of I from the appendices. And we'll write R loc of I to denote all locally integrable functions on I. And this will be a function space I'll refer to at various points in technical statements of different theorems. So let's start out with the function f that is locally integrable on all of the real numbers. It's an R loc of the reals. How do we define the integral from minus infinity to infinity of f of x? This is how we did it in calculus. Well, first of all, because f is in R loc of the reals, we know that if I have numbers a and b in the reals, the integral from 0 to a of f of x exists, and the integral from a to 0 of f exists, and the integral from 0 to b of f exists, because these integrals are just taken over closed bounded intervals a to 0 and 0 to b. So now let's suppose we have two limits existing. We'll put I plus of f to be the limit as b goes to infinity of the integral from 0 to b of f, and I minus of f is the limit as a goes to minus infinity of the integral from a to 0 of f. So I have two limits. One as the upper limit goes to plus infinity, and one as the lower limit goes to minus infinity. And I'm assuming that each of these limits separately exists. Then we'll define the integral from minus infinity to infinity of f to be the limit I plus on f plus the limit I minus on f. And in this case, we say that f is improperly integrable on the reals. We do not write, and I cannot overstate how important it is to remember this, we do not define the integral from minus infinity to infinity of f to be the symmetric limit as r goes to infinity of the integral from minus r to r of f. So if f is locally integrable on the real line, then yes, the integral from minus r to r of f exists for any finite number r, but it's possible for this symmetric limit to exist, say for f of x equals x, but I plus or minus on f don't. So the symmetric limit as r goes to infinity minus r to r of f could exist, but the I plus and or the I minus limits don't have to exist. Later, we'll come back to the symmetric limit in a couple of contexts where it is more useful. But remember that in principle, one always has to check the limit as b goes to infinity and the limit as a goes to minus infinity of those two integrals. And now we'll introduce another function space into our collection. I'll take a number p greater than 0, and I'll put LP on R is a set of all locally integrable functions on R, such that the modulus of f raised to the power p is improperly integrable on R. We are going to use this function space a lot, so maybe hit pause and make sure you've chased through its definition. And we're back. So f is in LP on R if and only if the improper integral from minus infinity to infinity of the modulus of f of x raised to the power p converges. And now let's look at some properties of the improper integral and these LP spaces. So this is theorem B.0.3. If f is improperly integrable on R, then gloriously the symmetric limit from the previous slide does exist. So if you know a priori that the function's improperly integrable, then its improper integral from minus infinity to infinity is given by the limit from minus r to r of the integral, the limit as r goes to infinity of the integral from minus r to r. Be careful with the flow of logic here. If those two limits, as you go to plus infinity and as you go to minus infinity separately on the previous slide exist, then the symmetric limit exists and the improper integral is equal to the symmetric limit. The reverse, of course, is not true, just taking f of x equals x. Another hugely useful and important property is the comparison test. Say you have a function that is locally integrable on R, and you have another function that is improperly integrable on R. So the locally integrable function is f, and the improperly integrable function is g. And suppose you have the following inequality. 0 is less than or equal to the modulus of f of x, well, that's always true, and the modulus of f of x is less than or equal to g of x for all x. So the modulus of f is bounded above by g. Then both the functions f and modulus of f are improperly integrable on R, and you have the following chain of inequalities. The modulus of the improper integral from minus infinity to infinity of f is less than or equal to the integral from minus infinity to infinity of the modulus of f. So first, I was able to pop the modulus inside the integral. That's the triangle inequality for integrals. And both of these integrals exist because f and modulus of f I claim are improperly integrable. And the second integral minus infinity to infinity of modulus of f, is bounded above by the integral from minus infinity to infinity of plain old g of x. So this sort of comparison, as we have for series, the sort of domination, if I know that the modulus of f is bounded above by an integrable function g, I get integrability of f. We will use this quite a lot. It's a really nice property. And 3, if our exponent p is greater than or equal to 1, then the function space LP of R is a vector space. What does this mean? If f and g are in LP, that is, if modulus of f to the p and modulus of g to the p are improperly integrable, then their sum, modulus of f plus g, is improperly integrable. So we can add these sorts of improperly integrable functions and get improper integrability of the sum. And I'll often use the words LP norm. We had some readings on norms that were optional right now, and they'll remain optional for a little bit longer. For now, we can just accept that the LP norm of a function f in the space LP of R is the following quantity. It is the integral from minus infinity to infinity of the modulus of f of x raised to the power p. You take that whole integral and you raise it to the power 1 over p. So we encountered LP norms in our discussion on the convergence of Fourier series and what's the right function space. Now we're just taking the norms to be, or the integrals to be over the entire real line instead of a closed bounded interval minus p to p. So frequently I will use the L1 norm and the L2 norm in some calculations and statements, so you should know that means this integral on the right here at the bottom of the slide with p equals 1 or p equals 2. And now let's do an example. Let's show that the function f of x, which we'll define to be 1 over 1 plus x squared, is in LP of R for all p. So what do we have to do? First, we need to be sure that f is locally integrable on R. And we look at f, 1 over 1 plus x squared. It's a rational function. The denominator is never 0. F is continuous on the reals, so f is locally integrable on the reals. And we also know that f is always positive. In particular, modulus of f of x is just equal to f of x for all x. And we'll start out by showing that f is in L1 of R, and then we will use a comparison test and be sneaky at the end. So we need to show that the improper integral of f over the whole real line converges. So let's first look at one of the integrals involved in that improper integral. We'll compute the integral from 0 to b of dx over 1 plus x squared. And we know from calculus this is arctan of b minus arctan of 0, and of course that's just arctan of b. And so the limit from calculus as b goes to infinity of arctan of b is pi halves. And so as well we have the limit as a goes to minus infinity of the integral from a to 0 of dx over 1 plus x squared equals pi halves. And this tells us that the integral from minus infinity to infinity of the modulus of f exists. Now as a quick calculation, so let's be sure we see what we did. We looked at the integral from 0 to b of modulus of f. We calculated that. We took the limit as b goes to infinity. We looked at the limit as a goes to minus infinity, and we calculated that. Both of those limits exist, so the integral over the whole real line also exists. So that shows that f is in L1, but what about the rest of those powers p? If we try to compute those integrals of f raised to the power p, we're going to have some problems, I think, getting a good antiderivative. Instead, we'll use the comparison test. For all x in the reals, we know that 1 is less than or equal to 1 plus x squared, right? Because x squared is non-negative, so we have this inequality. And that forces 1 over 1 plus x squared to be less than or equal to 1. So then when I raise 1 over 1 plus x squared to the power p, that is bounded above by 1 over 1 plus x squared. And so by comparison with the integral of 1 over 1 plus x squared, we know the integral from minus infinity to infinity of dx over 1 plus x squared raised to the power p also converges. And so f is indeed in LP for all p.